Hello and welcome to part one of 2 videos for our logic unit. This is our introduction to sets. So in this example, we have a universal set. So when you see the indicator U, that's usually talking about the universal set. And what that is saying that the universal set includes members that are all the integers from 1 to 9. So what we have to do is kind of create this universe or this box where we see all of the integers from 1 to 9. And within that universe, there's going to be 3 more sets. There's going to be set C, S, and E. So set C are all the curvy numbers. And these brackets themselves are curly. They would be sort of looking like this. So as you're writing them, please don't try to use the rounded brackets. You try to, simulate as best you can something like the squiggly, those curly brackets. So we have a set C within the universal set. That's representing curvy numbers. We've got set S that represents numbers that have some straight edges to them. There's a possibility that there's some numbers that have curves and straight edges. And then we've also got a set E, which is even numbers. That we can see. So we have our 3 sets there, and now what we'd like to do is just kind of place all the numbers into those sets. So for curvy numbers, member 2 is a member of the set of curvy numbers, and it's also a member of the set of even numbers. So we can represent 2 right here. So it's showing that it's within the set of the curvy numbers and within the set of the even numbers. 3 is not within the set of even numbers. It's just a curvy number, and it's not in the set of straight numbers. So I would put 3 here. 5 is both curvy and straight. We can see it within both of those sets, but not even. And so I'm just going to go through sort of the rest of the numbers and kind of fill them in. Otherwise we'll be 10 minutes watching me do this. Okay, there we go. So you can double check for yourself if you'd like, but these, let's say 4 is within the set of even numbers, also within the set of straight numbers, but not inside the curvy number circle. So I have some questions that we can ask ourselves about these sets. So now that we know what's inside the sets, we can ask ourselves, could we create an equal set to E? So here we have 2, 4, 6, 8 is one descriptor of the set E. An equal set has all the same members. It just might be in a different order. So that would be an example of an equal set to E. So different order, but same members. Equivalent set to E has to have the same number of members, but not necessarily the actual same members. So an equivalent set to E needs to have 4 members in it. It should be in the universal set, so let's do that. So you can have some original members, but it's not exactly the same members, just reordered. There's another symbol here. There's lots of symbols in logic. And to me, it looks like the euro symbol. It's like an elongated E. And that symbol means is a member of the set. So this statement is saying 3 is a member of the set C. And when we look at the set C, we see that 3 is, in fact, a member of the set C. So we could say that's true. 4 is a member of the set C. If we look inside the set, we look at the contents of the set, we would say that that is false. 4 is not a member of the set C. And if we wanted to say not a member of, that's supposed to be there, we would use this little sort of line that goes through it. So 3 is not a member of the set C. Well, that's not true because it is. So 3 is not a member of set C is false because 3 is a member. 4 is not a member of set C. That is true. All right. You can see this is not for the faint at heart. Okay, so we have then subsets. So subsets are like taking, let's say, a group like set C and making a subset. One subset could be 3, 6, 8. Another subset could just be a subset that includes a 3. So there's so many subsets, and one of the shortcuts is to have to the base 2 and then the number of members of the group. So in this case we have 6 members, and that let's equals 64. So 2 to the power 6 means 64. So if we were to write out all the subsets of set C, we would have 64 unique subsets. Again, please take a look through the notes. There's so many possibly better examples than these. But this is just meant to support the notes. So here I've created 3 additional sets, a set H, J, and M. And I'm asking the question with relation to E. So with relation to E, is E, this guy with this little, this is like an elongated C. This is asking, is E contained or properly contained within H? Is E properly contained within H? So are the members of the set E within the greater set H? So we're looking for something that looks like this. So if you have items outside, then you could use this symbol. If every single member of the original set is within the subset, then we would use this symbol to say contained within. This is saying properly contained. And you go based on how, which direction it's opening towards. So this is E is properly contained within H. And we look at H and we look at E and we say, no way, there's definitely members of E that are outside of H. It's not a subset of the greater one. So that's definitely false. Is H properly contained within E? So all the members have to be within E, but it doesn't have to be all of E. So I would say no, because the 1 and the 3 are not part of that. So H is not a subset or is not properly contained within E. Is J a subset, or is J properly contained within E? So 6 and 8, we see 6 and 8. We could imagine that sort of 6 and 8 could be here, this little subset of J within the greater set of E. So that is true. Now, is E properly contained within J? So are all the members of E a subset of J? Absolutely not, because we're missing 2 and 4. So it does depend which direction that you're going. And then lastly, with the little line underneath, means that all the members are within. So is it fully contained within? So M, is it fully contained within E? And we would look at that and we'd say, hey, this is actually the equal set. So yes, everything in M is contained within E. So that, in that case, is absolutely true.